The next item on our agenda then is to help us understand the second piece, which is for us to try to begin to understand what actually constitutes like one of these histories, and in particular, what are these events along my histories. So and to understand what those mean, it helps to have a little bit of a more concrete example. So there's a specific example that we are going to solve. So we are going to introduce then, as I had said, the nature of the fundamental events in histories. So fundamental events, E, right? And describe what these histories represent. And then we're going to prove that these two approaches are identical to one another. Now, to kind of draw out and understand really what these fundamental events are, it helps to have a specific concrete problem in mind. So what we're going to do is we're going to leave a little bit of space here in our notes where we can describe exactly what these fundamental events are. And then we're going to actually move a little further ahead in our notes. So you may want to leave a little space in yours to lay out the specific problem that we intend to solve. And that will help organize our thinking about the fundamental events. So let's consider a particular problem, right? So let's see here. So I'll start about here. So I'll have some potential v of x that I will be considering. And we're actually going to look at a problem that we've actually solved on a problem set assignment. This here then, this location of course is x equals 0. And I'll have a potential that is 0 for x less than 0. Then at x equals 0, it's going to take a discrete step upwards. And we'll have a different value. You can call that v0. And make it a little bit long as I go along here, right? Coming down to a point x equals a, where the potential then will become 0 once again. And I'm going to be trying to solve for what happens when I send in now a unit wave on this side. And I know what I expect then, of course, is to get some reflected wave. And I will call the amplitude on that capital R, like we've been doing. And up here then, the rest of my solution is this transmitted piece. And our job then is going to be to solve this problem. Now, in here, where I have this constant potential, it might have a certain height. Let's call that v0. And I then have different wave vectors in these two different regions. So I start with 0 potential. That's a type 1 region where I have k1. Here in region 2, I will have k2. But back over here, because I've come back to 0 potential, I'm back to k1. I'm back in a type 1 type region. Now, if we think about this problem physically, we begin to get a sense for what I mean by histories and events. Because after all, if a particle is going to be sent in from this side and eventually, say, be transmitted out on this side, what has to happen in between would be that the particle gets transmitted across this up step. It then propagates across my system, and then it has to then transmit across this downward step. So those are the types of events that we're talking about as the fundamental events. So, for example, the first fundamental event we need to consider would be, okay, I have an up step in potential, right? So here's a v of x, right, where I go from a type 1 to a type 2 region. This is v of x versus x. And notice now the potential I'm talking about just extends out to infinity as constant to the left and to the right. The particle, when he first hits this up step, has no idea about what's going to happen to it in the future over here. So I'm really just concerned about this location here near x equals 0. Now, this is a type of problem that's much easier to solve, of course, than this composite step. This was a little bit of a pain in the neck to solve. This case was actually relatively straightforward. Now, we had actually solved this in a previous lecture, and there was a unit incoming wave, right, a reflected wave, and a transmitted wave that results. And we can call then these corresponding coefficients, because these are not the total net coefficients, so I will use lowercase letters. This would be the amount of transmission, and this would be the amount of reflection. And when we had solved this, we actually found the values for these coefficients. So the reflected piece, you might remember, was k1 minus k2 over k1 plus k2. Now that's what we had found in our lecture when we were working with that old normalization convention. We have to be careful because these symbols represent pure plane waves that have a slightly different normalization. But fortunately, as we had just discussed over here, the change in the normalization does not affect the reflection coefficient. So that I can just recycle the old expression that I had had. There's also, though, of course, the corresponding transmission coefficient, and I will write that here, T, right? And that turned out to be twice K1 in the previous lecture over K1 plus K2. But now again, that was under the old normalization convention. Under the convention that goes with these wiggly lines, the transmission coefficient picks up an extra root of K2 divided by K1. So there'll be an extra square root of K2 over K1. And one thing that's kind of nice about this factor is if you multiply it through, you see you get something nice and symmetric. It's the square root of K1 times K2. Very good. So that's the answer that we need for that first type of an event. We also have the event where we are transmitted when we go across this downward step. That's a slightly different potential that has a different answer associated with it. So let me draw, what that potential would look like. So now what I have is a step here, right, where I'm in a type 2 region, and then I go down this step into a type 1 region. And once again, I'm going to be sending some incoming unit wave 1. It will have some reflection, which I'll call R, and some transmission that I will call T. Now notice, though, that this process is different from this one. In this one, I'm impinging on an upward step, whereas here, I'm impinging on a downward step. So these will have different answers from those. So I need some way to denote that. Since this is an upward step, I will refer to these with positive numbers for upward step. And these I will put negative subscripts to represent a downward step. So the answers I've given here are really for the positive versions. Now, to get the negative versions, we can play a little bit of a trick here. Because after all, this is just scattering from one value of k to another value of k. It's essentially the same thing. It's just now I'm going from a region 2, a K2, to a K1, instead of from a K1 to a K2. So I can just recycle these results, switching K1 and K2. If I do that, this first term, the denominator doesn't care about the switch, but the numerator would care about the switch. So the result is positive when I'm talking about the positive reflection coefficient. If I'm talking about the negative reflection coefficient, I pick up a minus sign. For the transmitting case, it's simpler actually. If I swap K1 and K2, then neither the numerator nor the denominator cares. So this values would work T plus or T minus. So those are the two types of events that we know about so far. We're going to be coming back if we learn that there are any others. But let's now begin to think about the actual problem that we're trying to solve here using these ideas. So, okay, so let me just kind of bring these boundaries downward so I can represent my solution. So the idea is I'm going to send in, so here I'm going to try to write, the final solution. So I begin by sending in a unit wave. Now, as soon as I've drawn this picture, I have a problem. Because in my notation, what this represents is that I've got a unit incoming wave on this side and 0 over here. There's nothing in between here. Because of that, there's no way I can match the boundary condition across this dividing line. Consequently, then, I need to include some additional pieces, and I know exactly what the pieces should be here that would satisfy my boundary condition for an up-step scattering event. I need a transmitted and reflected pieces with coefficients T plus and R plus. So there's going to be an outcoming wave here with amplitude T plus, and there will be then a reflected piece coming backwards with amplitude of R plus. Very good. And now I've completely satisfied this boundary condition. But unfortunately, I now have some difficulties because now notice I have a wave in this interior region, but nothing represented outside here. So I have 0 out here and a wave on this side of this boundary. I can't satisfy the boundary conditions on this side. Now, I do actually know how to satisfy those if I have a unit incoming wave over here like so. And then whatever amplitude it has would then generate, of course, a final transmission that will be whatever the prefactor on this wave is times t minus, right? Because it's a linear equation. And then similarly for the reflected component. And when I do that, I will have satisfied the boundary condition over here. Now, to get these factors, I have to be careful about one thing, right? This wave here represents a wave in region 2, but it denotes by my notation something slightly different from what this wave is. And I need it in the form of this wave because this wave is where I actually know the answer for the scattering problem. So I have to think about what happens. So I'll draw a diagram here to represent this, right? When I have these 2 points here at 0 and A. What happens if I have a unit wave represented over here by the time it comes over and is represented like this? So the first piece, right, I'm going to write the corresponding equation over here. This first piece represents a wave e to the I kx divided by root, that's k2, h bar k2 over m, right? That's what a unit wave in this direction would be. The unit wave in this direction would represent e, or on that side, k2, but it's now centered at a different location, x minus a, divided by square root of h bar k2 again over m. And these two are not equal. I can't say that this unit wave here equals this unit wave over here. I can make them equal, though, if I include one additional factor, right? This has this extra e to the minus I k2a. So I'd have to multiply this by an additional e to the I k2a. Then I can claim that these two pieces are equal. So I just need to include this particular prefactor. Now this, evidently, is the effects of my particle propagating from this location across my barrier. So I'm going to denote that as a new fundamental event type parameter. I'm just going to call that P. And I have this nice equality that a one wave over here equals P times the wave that's touching location A. With that in place then, I know that what I have incoming over here is not just T plus, but it has to include that extra factor that goes to equate my functions. So this will be T plus P. And now that I know this incoming portion, because my equation is linear, I know proportionately then the outcoming wave would be T plus P times a transmit minus, because I'm transmitting across this downward step. And the reflected piece back then would be the incoming amount T plus P, but it now carries a reflection off of this downward step, so that would be an R minus, like so. So at this point, I've now satisfied my boundary over here. But yet again, I'm not quite done, because even though these terms are in balance, right? These terms were in balance when there was no backward wave in region 2. But I now have a backward wave in region 2, which disturbs the balance of the boundary condition on this side. Now, when I think about it on this side, right, I know that I can re-satisfy the boundary condition here by including then the two pieces needed to solve the boundary condition problem, which will look something like so. And now I need to determine two things. First, I need to know how the wave on this side, backward traveling, maps onto the wave on this side, backward traveling. And I also need to know the corresponding transmission and reflection coefficients. So let's take those one at a time. And by that point, we will then have all of our important Feynman parameters and have completed what are called the Feynman rules. So first, what if I have a backward traveling wave over here? What do I need to do to make sure it matches up with the backward wave hitting at 0? Once again, I can write down my equality. So on this side, I have e to the minus I k2x divided by square root. You can see why we like the diagrammatic notation. Writing all these square roots just drive you crazy, right? That represents this term, right? And I want it to equal, it'll probably need some prefactor. It's going to equal then 1 times the backward traveling wave. So I want that equal to 1 times e to the minus I. This is k2, but this symbol is centered at a, x minus a, divided by the square root of h bar k2 on m. And we can see again, these are not in perfect alignment with each other. What I'm missing is the fact that this term has an extra e to the I k2a. So I can regain equality if I include that factor, e to the I k2a. Now I've established equality. This factor, notice, is exactly the factor p again, which is convenient. So I only need one of these propagation factors. So evidently, when I propagate from side A back to 0, once again, what happens is that I pick up an extra propagation factor, p. Therefore, the incoming wave on this side now has a whole series of these factors. It came from here, so it has the t plus, which notice there's a nice interpretation. That came from the first transmission. Then it propagated across and reflected. So I've got those pieces of my history, propagated across and reflected R minus. Finally, I have to include this extra p because I've now propagated back across, right? That's just this identity here. And that's my incoming component. And that finally then contributes. Oh, now notice I have a different type of scattering event I haven't seen before, when I'm scattering coming in from the left on this upward step. So that then I will denote as yet another scattering event. So what I'm hitting then is this upward step. Right? I'm coming back and I'm hitting my upward step, but I'm coming in from the backward direction. Right? So I have an incoming 1, which then would generate some reflected piece and some transmitted piece. And I need now to know the amplitudes from this. Now, there are really two ways to see what these amplitudes should be. The quick kind of way is to see, well, it's the same kind of scattering event. I'm going from a type 2 region to a type 1 region. So therefore, it should be very closely related, actually, to the previous event. Right? So you might guess, if you were a guessing person, well, I'm transmitting and reflecting off of a downward step. I would expect I would get still, again, R minus and T minus. If you want to be more rigorous about this, you can actually show that, well, if I just change my x-axis from forward to backwards, that would map these two pictures onto each other. So therefore, they should, in fact, just have exactly the same coefficients. If you want to think about it a little more rigorously, you could say, well, if v of x goes to v of minus x, then by symmetry, my phi of x would have to map to my phi of minus x. And because this flipped around picture actually represents exactly this phi of minus x, and the potentials are exactly flipped, these should be exactly my coefficients. So, long story short, I'm just transmitting or reflecting again off of a down step. So the transmitting through here would give me a t plus pr minus p and a final t minus, because I'm transmitting when I'm hitting a downward step. And then my reflection coefficient then is t plus pr minus p. And now I'm reflecting off of what to me looks like a downward step because I'm coming in this direction. So there's a final r minus once again. And now my boundary conditions are perfectly satisfied on this side. But you can start to see then the overall behavior that we will experience. In particular, you will notice that I've now satisfied this side, but I've disturbed the boundary condition on the far side. So this wave will again propagate across. We know what that would mean. It's going to be the same factors here, but there'll be an extra p for that extra propagation event. And finally, there will be an outcoming piece and an incoming piece generated, which will satisfy the boundary condition over here. And we can continue this way ad infinitum. Now, the one thing that really works for us here is notice that each time my wave bounces back and forth, it transmits a little bit more to the outside. So the amplitude of what's going back and forth in here is going to slowly shrink down to 0. So at the end of the day, by continuing this process into an infinite series, at the end I will actually have perfectly satisfied both boundaries because the wave bouncing back and forth becomes so very weak. Now that we have our basic form of the solution, I think it's good to sit down and write down the total amount of transmissions that we have and total amount of reflections very carefully.